Hello everyone and welcome to Related Rates and Optimization. Today we're going to start with related rates. So in related rates, we're going to have word problems that use implicit differentiation and the chain rule to find the rate of change of two or more related variables with respect to time. So what you're going to see in related rates a lot is the derivative of some variable with respect to time. So d something, dx, dy, d anything over dt. So we're going to start with an easy problem. This isn't a word problem, so you wouldn't see something like this on the test, but it's a good way to see how to do it. So we have y equals 2x squared plus 7, and then it says find dy dt when x equals 1, given that dx dt equals 3 when x equals 1. So you're going to start by taking the derivative with respect to time of the whole thing using implicit differentiation. So you have y equals 2x squared plus 7. You're going to take the derivative of the whole thing with respect to t. And the derivative of y is just 1, but because you're doing implicit, you're going to have dy over dt is equal to the derivative of 2x squared is 4x, and that's going to be dx dt. And the derivative of 7 is just 0 because 7 is a constant. So now that you have this equation, you look back to what it tells you in the problem, and you see that you can plug 1 in for x and 3 in for dx dt. So you have dy dt is equal to 4 times x equals 1 times dx dt equals 3. And that gives you dy dt is equal to 12. And what that means is that 12 is the rate at which y is changing when x equals 1.
Okay, so these are the steps for solving related rate problems. So first you want to identify all given quantities and quantities to be determined. Make a sketch and label the quantities. Write an equation involving the variables whose rates of change are either given or to be determined. And we have attached a link to just different equations if you don't remember them. And then using chain rule, implicitly differentiate both sides of the equation with respect to time t. And then you're going to substitute the resulting equation, all known values for the variables and their rates of change. Then solve for the required rates of change. And then on your final answer, don't forget to add your units.
Okay, so a bird and a bee leave a flower at the same time. The bird goes south at a rate of 80 miles per hour, and the bee goes west at a rate of 60 miles per hour. We're trying to find how fast the distance between the bird and the bee is increasing after 3 hours. So the first thing that you're going to want to do is draw your triangle. And so we know that the bird is going south at 80 miles per hour, so you're going to write down that. And then you know the bee is going west at 60 miles per hour, so 60 miles per hour. So you're going to want to find how far that distance is after 3 hours. So 80 miles per hour after 3 hours is going to be 240, so you're going to write that down. And then 60 miles per hour after 3 hours is going to be 180. And so then you're going to use the Pythagorean theorem to find out what the distance is at 3 hours between those two. And so 240 squared plus 180 squared is going to equal 300 squared. So this distance is 300. So now that you know all that, you can set up your related rates equation. So you're going to use the Pythagorean theorem again. So a squared plus b squared equals c squared. And so you're going to take the derivative. So it's going to be 2a dA dt plus 2b dB dt equals 2c dc dt, and you're going to plug in what you know. So you have 2 and then we're going to label the triangle A, B, and C. So A is going to be 240, and then the rate is 80. And then you're going to do B, so it's going to be 2 and then 180. And you know the rate is 60. And then we're trying to find C. So we know the distance, which is 300, but we're trying to find the rate. So you're just going to leave that as dc dt. And so once you do all the math, you'll get that this is 60,000, and then this is 600 times dc dt. So the distance, or the rate, is going to be 100 miles per hour equals dc dt. So the distance is increasing by 100 miles per hour at 3 hours.
So next we're going to be doing a related rates problem with a cylinder. This one says a cylinder filled with water has a 3-foot radius and a 10-foot height. It is drained such that the depth of the water is decreasing at 0.1 feet per second. How fast is the water draining from the tank? So I already drew a cylinder, but now we can use the information from the problem to label it. It says that the radius is 3 feet, so that's going to be a constant, 3 feet right there. And we know that the height of the tank is 10 feet. We don't know the height of the water, or the depth of the water, so we're just going to label that as y. But we do know that it's decreasing at 0.1 feet per second. And anytime something is decreasing, that's going to mean it's negative. So it's changing at a rate of negative 0.1 feet per second. Since it says how fast is the water draining from the tank, it's looking for the volume. So what we're looking for is dV dt. Because we're looking for the volume, we're going to want to use the equation for the volume of the cylinder. So that is V equals pi r squared, and it's usually going to be pi r squared h, but we're doing this cylinder, and we labeled the height as y, so we're going to have pi r squared y. So the radius is constant. It's going to be a constant 3 feet, so we can go ahead and plug that in and get that volume is equal to 9 pi y. And then we're going to differentiate both sides with respect to time. dV dt is equal to 9 pi dy dt. And over here we can see that dy dt, that's going to be negative 0.1 feet per second, or negative 1/10. So dV dt is equal to negative 9 pi over 10 feet cubed per second. And it's feet cubed because we're talking about how the volume is changing. So that's going to be your answer because the water is decreasing. So how fast is the water draining from the tank? It's draining at a rate of negative 9 pi over 10 feet cubed per second.